Today we're going to be discussing section 12.2, which is all about chords and arcs. So we're going to start by looking at a lot of our theorems. So we're going to take down quite a bit of theorems and their converses today. We're just going to start by writing a bunch of them down, and then we're going to do some practice problems with them. So if you have your theorem sheet, or if you're creating your own, we're going to be filling in theorem 12.4 through 12.10 right now. So you have an option, you can, just pause the video, you can write this all down, but I'm actually going to show you my filled in version. So if you want to pause the video, you can copy this all down right now, or you can come back later. I'm going to talk through what these theorems mean and why the pictures look the way that they do. So I'm going to go back to my notes. I'm going to talk through these. So in this first one here, this is two theorems and their converses together. So we took two individual theorems and we merged them into one with two statements in there. And you can see those two statements are labeled 1 and 2, but it says, okay, you have a circle, or you have two circles that are the same size, two congruent circles. This means the radiuses, the radii are the same size. So typically we're going to see this in, in one circle, but you could have two circles that are congruent to each other, that are the same. But we're looking at this, we say, okay, if they have this same size central angles, if they have congruent central angles, then they are going to have one congruent arcs. And we're going to start with that one first. So if you remember a couple units ago, we talked about arcs and how arcs have two values associated with them. They have an arc measure, which is an angle value or the degree value, and then they have an arc length. And no matter which one you're talking about, in our situation that we have here, since my two angles are congruent to each other, these two angles here at O are congruent to each other, these two arcs, either the measures or the lengths, whether I'm talking about measures or lengths, they are going to be congruent to each other as well. That's the first statement. The second one says, okay, you've got these congruent central angles, then you're going to have congruent chords. That's statement number 2. And before we get too far in that, we need to talk about what a chord is. So we're going to define a chord. It is a segment that connects one point on your circle to another. Which, okay, that's maybe not super helpful, but it says, okay, you've got a circle here. You want to connect, I don't know where my circle went. All right, we'll redraw it. I have my circle here. I want to connect one point on my circle to another. There's a chord. I want to connect, say, this one here. There's a chord. Chords can go through the center, but they do not have to. All right, so essentially you're just drawing a line, drawing a distance across your circle. So in our case here, if I look at my particular problem that I have, it says, okay, when I have these central angles, they are going to be going out to 2 points on my circle. If I connect those 2 points, so like we're cutting off the crust of our pizza slice, we have just created a chord. And if I do it over with my other angle and my other arc, I've created a chord, a second chord. And we are now saying these two chords, if my central angles are congruent, those have to be congruent as well. So this actually creates sort of a loop because the converses are true as well. So if I have congruent arc measures or congruent arc lengths, then I'm going to have congruent angles. Or if I have congruent chords, I'm going to have congruent angles. So we create this sort of system that says, okay, you have congruent central angles. Well, that's creating, and this goes backwards as well. I'm going to pick a different color for my arrows here. Goes in both directions, congruent arcs. And that's going to create, in both directions, congruent chords, which also implies, in both directions, congruent central angles. So this theorem is really two theorems and their converses. It creates this little cycle. You have congruent central angles, great, you have congruent chords. You have congruent chords, great, you have congruent arcs. You have congruent arcs, great, you have congruent central angles. And I can go in any direction. I can start anywhere and go in either direction I want from there. Now with this, because we're using a lot of the same variables, a lot of the same points for our names, we do need to be careful with our naming and making sure we're being clear with our labeling here. So central angles, this will be like angle in our particular problem here. COD is congruent to angle AOB. That one's not so difficult, or that one's not the one that leads to confusion. But when I get to my arcs, I have arc CD. I need to make sure I put the little arc above that is congruent to arc AB with the little arc above it. Because when I talk about my chords, I'm still going to use C and D and A and B with segment bars above them. So there is only a slight change in notation. I either have the little arc symbol or I have the segment bar. So I need to make sure that I'm being very clear and purposeful in my naming when I'm talking about these things. So I know if I'm talking about my arcs or my chords. Okay, but we have all three of these here together and we create this picture. And then we can talk about theorem 12.6 and its converse. This says, okay, within a circle or within congruent circles, congruent chords have congruent arcs. So this is saying, okay, you've got this picture here. What if I draw, I'm not looking at angles this time, but I'm looking at, say, these arc values, or excuse me, these chords here. And let's say CD is indeed congruent to AB. Well, that is going to imply, and this does the backwards direction as well, that arc CD is congruent to arc AB. This is actually just a variation on what we were talking about up above, but without including the central angle in there. Okay, so this is going chords, arcs, arcs, chords. So arc CD, and I'm going to do that in a different color, whether I'm talking about measure or distance, is congruent to arc AB. Okay, theorem 12.7 and its converse, same picture here. Or this 12.6 could actually be using this picture up here, and 12.7 uses this picture here. It says within a circle or in congruent circles, chords that are equidistant from the center are congruent. So this is saying, okay, I've got these two chords, A, B, C, D. If I look at the distance, so I measure how far away my chord CD is from center O, and then I measure how far away my chord AB is from center O. If those are the same, because that's what it means to be equidistant, you are equal distance away, then that's going to force AB to equal CD, or the chord AB to be congruent to chord CD. Theorem 12.8 says, okay, you've got a circle, and actually all three of these are using the same picture here. It says you have a circle. If, say, a diameter is perpendicular to a chord, and this diameter can be replaced with the word radius, so either diameter or radius is perpendicular to a chord, then it bisects the chord and the arc. So let's say, okay, we've got this here. I've got my chord, and I have my diameter, or I could have it just start at point H, and I could just be looking at the radius. This works as well. But if I'm going to have it be perpendicular, then I just bisected my chord. Those two pieces have to be equal. And I bisected my arc. So those two arcs have to be equal. That's what 12-8 is saying. 12-9, same situation. This is just going backwards. Oh, you bisect your chord, then you get to put a right angle in there. And then 12-10 says, okay, say I know I've got it, my chord is bisected and perpendicular, then I have to be on the diameter. That's what it means to contain the center of the circle. It means you're on your diameter. So all three of these are using the same picture, and they're all saying, okay, you've got a radius or diameter and a chord are intersecting. If they intersect at 90 degrees, your chord is cut in half. If they intersect so your chord is cut in half, then it's a 90-degree angle. That's essentially what's going on. So we're going to use some of these new theorems to solve some problems. Again, if you need to, you can pause the video. You can go back to when I had my theorem page filled out, and you can fill in your theorems and you can fill in your pictures. But we're going to do some practice problems now. So if I go down to number 1, I want to find the value of x. So I want to look at my problem and I want to sort of analyze the situation because we've already got 10 theorems written down on our theorem page. So we have to figure out which one works the best. So I want to see what I've got. I have chords and I have distances from the center to the chords. So I want to take a look back at my theorems and say, okay, which one has a picture that looks like this or has these things, a center and distances to this from the center to the chords? So if I look, that's going to lead me up to this theorem 12-7. 12-7. And it says, okay, if I look at my two chords are equal to each other. My two chords are both 36, which implies from theorem 12-7 that the two distances from the center to the chords should be equal to each other. So that implies x equals 16. And we're done. There is no algebra problem to solve. We will have some later, but x equals 16. We're done. All right, example number 2. Again, I want to look and see, okay, what sort of problem do I have here? Here I have a chord, but only one. Don't have two. So theorem 12-7, remember that's involving two chords. 12-6, 12-5, 12-4, all involving multiple chords. I don't have multiple chords. I only have one chord. So this is going to put me in the 8, 9, or 10 region. 8, 9, and 10 are all using that same idea that says, okay, you've got a chord and you've got the segment connecting to the chord. So if I wanted to keep going, I could make this into a radius or I could make this into a diameter if I kept drawing it. I don't have to. But if I look, I say, okay, my chord got cut into two equal pieces. My chord was bisected. So I'm going to look and say, okay, which of these has to do with chords being bisected? And I'm going to say, well, 12-9 has bisects a chord in there. So I'm going to read 12-9. It says, in a circle, if a diameter bisects a chord, then it is perpendicular to the chord. I have a diameter or pieces of a diameter. It's okay if it's not the full thing as long as it's pieces of my diameter. If I were to finish drawing it, that would be my whole diameter. It's bisecting my chord. 12(9) says, well, I get to draw a right angle in there. And now I can say, okay, well, I've got this extra piece from E to B, that's 15, but I've got a dotted in segment from A to B. That also has to be 15 because both BE and AE are radii, which means they have to be the same, which means we just created a right triangle. And we know how to deal with right triangles. So what I'm going to use is my handy dandy super friend, not quite my best friend, but I'm going to use Pythagorean theorem. A squared plus B squared equals C squared, where I have y squared plus 11 squared equals 15 squared. And by doing that, working that whole thing out, I get y squared equals 104. So I square root, and we are going to, I'm actually going to leave this in simplest radical form just to practice that. If the directions on your homework say round, then put it in your calculator and get a decimal. But I'm actually going to say, well, this breaks into 4 and 26, which that is 2 and 2. This is 2 and 13. So I'm going to say y equals 2 root 26. And there's my answer. Oops, I'm going to change that box. There we go. See it a little bit better. All right, so when you start to see these types of problems, you want to figure out which theorem are we going to be using, because we've just introduced a lot. So you want to look at the situation, think about what you have, what you know, what you're trying to find, and find the theorem that best fits. So sometimes that means looking for the picture that looks the most similar. Sometimes that means looking for keywords like bisect. But if I go to the next two problems, 3 and 4 here, if I start with 3, again, I have this diameter, and this diameter is perpendicular to a chord. So a diameter perpendicular to a chord sounds a lot like theorem 12(8). I'm actually going to double check that it is 12(8). There we go. Theorem to perpendicular chord, diameter. Diameter perpendicular chord is theorem 12(8). That means my chord is bisected, or 12x plus 7 equals 3x plus 16. We can solve for x. So we get 9x equals 9, so x equals 1. And all I'm being asked is to solve for x. They don't ask me to go back and find any distances or any lengths. Remember, we always want to double check and say, what is the question actually asking? This one just asked for x. We found x, so we're good. We don't need to plug it back in. All right, last example before we do a couple more theorems is example 4. Again, try and figure out what situation we're looking at. So this is, okay, I have 2 chords now. So 2 chords implies 12, 4, 12, 5, or 12, 6, or 12, 7. All 4 of those, 4, 5, 6, and 7, deal with 2 chords. In these 2 chords, I don't know my arcs, I don't know my angles, but rather I know these distances here. So this is going to most likely be a 12-7 theorem type problem. So because my 2 chords are equidistant from the center, 12-7 says that the chords are equal. ST is equal to VU, or 6x minus 5 equals 13 plus 4x. So 2x equals 18, x equals 9. And again, the question says the value for x. It doesn't ask me to find ST or VU, but I get x is equal to 9. Okay, so these 4 problems, you have to look at your picture, look at your situation, and say, okay, which of the above theorems fits best for what I'm doing here? And then use that to help you solve. Theorem 1215 is what we're going to fill in next, and this is actually down at the very bottom. If you printed off your theorem sheet, and I'm going to go to there right now, is down at the very bottom because we put them in order of their numbering, 1 through 15. We actually see it earlier in the unit than some of the other ones. If you're creating your own, you can put this in wherever you want, but there are 3 different situations that are occurring in Theorem 1215. Okay, so that has to do with these chords lengths and these secant lengths and these tangent lengths. All right, and so I color coded on my theorem page to help me keep track of my pieces and all of that. I'm going to go back to my note page in just a minute. If you want to pause and write this down, you can. Otherwise, I'm going to go back here. Same thing. This one's just not color coded here, but I want to talk through it. So in this first one here, I have 2 chords intersecting. And each chord is cut into 2 pieces. So I have 4 pieces of my chords. And I'm going to label A and B as 2 pieces from the same chord. So A and B both come from the same chord. And then C and D both come from the same chord. So these are like pieces of diagonals and other things in polynomials or polygons. Not a polynomial, excuse me, but a polygon. Here we're looking at circles. So they don't really call them diagonals because you don't have these corners, but we do call them the chords. And it does create a relationship between their distances. A times B, both of these from the same chord, so those come from the same chord. When I multiply, that product is equal to C times D, those 2 from the same chord as well. Theorem 1215 is using what we call 2 secant lines. So secant lines are pretty much like extended chords. So you take those chords and you go outside. So you're intersecting your circle twice and you have pieces that are outside of your circle. And so now instead of intersecting on the inside, we've created each secant line has 2 pieces. It has an inside piece and an outside piece. And then if I added the in and out together, I create a whole segment. So what's happening here is you're always taking the outside piece times the whole segment from one secant line. That product is equal to the outside piece times the whole segment on the other secant line. So it's always outside times whole equals outside times whole. And then the third situation has 1 tangent line and 1 secant line. Oops. So remember, your tangent line is going to brush up against the outside. It will never enter your circle. So your outside piece is the same thing as the whole piece. They are the same thing. There's no difference between them. So what changes is we still have outside times whole, but for the tangent, that's both A, so it's A squared, or outside squared equals outside times the whole piece. So that's the same thing that's happening. Outside times whole equals outside times whole. Okay, so theorem 1215, it's all about the intersection of lines and chords and segments. How it looks, this is really going to be like which picture looks the best. And you can rotate these. You can definitely have these be flipped around, upside down, but are you looking at, are we intersecting inside the circle? Are they intersecting outside the circle with two secant lines, or is it one secant line, one tangent line? And then follow your setup. So if I look at my first example here, this very clearly, oops, is matching my first. This is two chords intersecting. So what I'm going to do is I'm going to look at my pieces, and I remember A and B come from the same segment, C and D come from the same segment, and I can just label some. So then I have A times B equals C times D, or for our particular problem, x plus 4 times 10 equals x plus 1 times 15. And we're going to solve by distributing. So I get 10x plus 40 equals 15x plus 15, or 25 equals 5x, so x equals 5. And I should have done this up above, but I do want to go back and make sure that this actually makes sense. All right, because I'm dealing with distances, I'm dealing with lengths. So if I plug in 5, I get 9 here. I can have a segment that's 9 units long. If I plug in 5 here, I get 6. I can have a segment that's 6 units long. Yes, my picture is definitely not drawn to scale. That's okay. Pictures not being drawn to scale might bug us, but there's nothing wrong with that. We're looking for, are my distances positive values? That's what we're looking for when we do this check. But I get x equals 5. Second example, you can see this looks like our second picture in the middle of theorem 1215. This is two secant lines. So when I do this, I can look at A times A plus B or B times whatever, but I like to just think of this as the outside times the whole segment equals the outside times the whole segment. So I need to think about how would I describe the distances for the whole thing. And on the bottom segment, that's a little easier. That whole thing is just 10. Top is a little bit more involved. That's going to be x plus 5. So when I go to set this up, I'm going to have 5 times x plus 5 equals 6 times 10. Then we can solve. 5x plus 25 equals 60. 5x equals 35. So x equals 7. And if I look, x is my actual distance, and I can have a distance that's 7. And that's fine. All right, last 3, I'm going to go through them. If you want to pause and try them yourself, you can, absolutely can, but I'm going to work through them right now. So number 3, this is our third possibility. This is the tangent and the secant. So outside is the whole thing on the tangent. I can still start with that same idea of outside times whole equals outside times whole if I want, but when I get to here, my outside and my whole distance are the same thing. So that is the same as outside squared. So either way I want to think about it, it's going to work. The whole distance on this secant is going to be 11. So I get y squared equals 2 times 11, or y squared equals 22. So square root, y is going to equal 4.7. Let's do 1 decimal place, 4.7. And again, if you do 1 or 2 or 3 decimal places, or you do simplest radical form, that's just going to depend on your directions, whatever your directions ask you to do. All right, same thing in number 4. Same exact picture, it's just flipped around. This time my whole distance here is 12. So I have x times x, or x squared, equals 5 times 12. So x squared equals 60, square root, x is going to equal 7. Oops, 7. All right, so far fairly straightforward. So far, if I go and I check, yes, those are both positive values. Yes, my distances are okay. Number 5 is a little bit more complicated. Number 5 is that middle picture. This is 2 secant lines. So we're going to have outside times whole equals outside times whole. That's my setup. That's my equation here. I need to come up with something to represent the entire distances. So if I look at the first segment, the one across the top, the whole thing is going to be 3 plus x plus 2, which combines and gives me x plus 5. My bottom one is going to be x plus 1 plus x minus 1, which combines to give me 2x. So I'm going to have 3 times x plus 5 equals x plus 1 times 2x. When I start multiplying and distributing things, I get 3x plus 15 on the left equals 2x squared plus 2x on the right. I have a quadratic. We need to solve that. So I'm going to set everything equal to 0, or 0 equals. So I'm going to move everything from the left over to the right. So I'm going to subtract 3x. I'm going to subtract 15. Combining like terms, I get 0 equals 2x squared minus x minus 15. And I am going to factor this. So I'm going to build my box. And I'm going to start by filling in my first term. Come on. And my last term. So my first term is 2x squared. My last term is negative 15. To figure out what goes in the other two, I got my x here. My multiply number is negative 30, because remember it's a times c, so 2 times negative 15. My add number is negative 1. So build your list however you want to come up with it. You should get negative 6 and positive 5. So I have negative 6x, positive 5x, and let's do some GCF. So I get negative 6 and an x, 2x, and a 5. So this gives me 0 equals 2x plus 5 times x minus 6, or 2x plus 5 equals 0, and x minus 6 equals 0. So x equals negative 2.5, and x equals positive 6. And we need to check and say, do those make sense? Because remember, these are actual distances, actual lengths in our segments. So I'm going to start by testing the negative 2.5 and say, okay, if I use negative 2.5 in this segment that I just highlighted in orange, I have negative 2.5 plus 2. That's going to give me negative 0.5 back. That's a problem. You cannot have a distance that is negative. This is saying, oh, well, that distance is negative half of a unit. That does not work. I don't need to check anymore. As soon as I get one distance that's incorrect, that's a negative, I say, oops, that's an extraneous solution, and we ignore it. I need to check my other one. I need to see if this picture is even possible, or if they're both extraneous, or if one of them works. So I tested that. Let's test the next one. If I test x equals 6, then that tells me this distance here is 8. I can have a distance that's 8. So it works for that one. I have to check my other ones though. It has to work for every place I have an x. So let's go out here with the x plus 1. That gives me 6 plus 1. That gives me 7. That works. It might not look like it because it may not be drawn to scale, but 7 is an absolutely acceptable answer for a distance. My last one is this piece right here, where it's x minus 1. This would be 6 minus 1, or 5. And again, might not look like it because we're not drawn to scale, but 5 is definitely an okay segment length to have. So every segment that included an x, I tested them all. 6 works for all of them. So 6 alone is my answer. Now, if negative 2.5 works and produces net positive distances, we would keep them both. But because that created an issue with at least one segment, I ignored it. All right, so a lot went on here. We practiced some extraneous solutions there at the end, but we have a lot of theorems that we wrote down. So theorems 12.4 through 12.10, and then 12.15. All right, so if you're filling out the sheet, the 12.15 is down at the bottom. If you're creating your own, you can put that wherever you want. This PDF is going to get posted to Schoology, so you can look at it again. And then, as always, if you have any questions, please don't hesitate to ask.